Okay, welcome back, everyone. So this is our last session in today's seminar. We have two very interesting talks. The first one will be given by Professor Yiran Chen. He is an external speaker. And after this talk, then Steve Crago will talk about some opportunities for AI and the DoD recent microelectronic commerce program. Let's start first with Professor Yiran Chen. And I know Yiran for over a decade. We have collaborated on a number of projects. And he has a long resume with a lot of things worth highlighting.
I don't have to read them.
For the time's sake, I'm going to just mention a few things. Yiran got his bachelor and master degrees from Tsinghua University, and then his PhD from Purdue University. And he actually worked in industry for 5 years after that. And he's currently a professor in the ECE department of Duke University. He also served as the director of the NSF AI Institute for Edge Computing, leveraging the next generation networks. And his group focus on the research of new memory storage systems, machine learning, and neuromorphic computing, and the mobile computing systems. He has published one book and over 500 other technical publications, and has 96 US patent granted. And he's editor-in-chief of IEEE Circuits and System magazine. He obviously received a lot of awards. He's also a fellow of ACM and a fellow of IEEE. And today he's going to tell us AI to advance edge computing for next generation networks. Okay, Yiran, please.
Joshua, thank you so much for the introduction. Also thank you so much for the invitation from you and also Yolanda. I will be very honored to share some information about our AI Institute and also the research of my group relevant to the edge computing. As Joshua just mentioned, we were granted this AI Institute for Edge Computing 2 years ago. I want to give people some basic idea about what we're doing here. So this is some background about why people created this AI Institute. Back to a few years ago, the White House, they decided to make a long-term investment on the AI research. As a part of the plan, NSF, together with some funding agencies and also industrial partners, to launch this called National AI Research Institute. So far, there were actually the 19, now 18. This is the old slides. Recently, they granted one more. It's basically the 19 AI institutes have been granted. The first year, 7, the second year, 11. Each of them received roughly $20 million for 5 years, and they currently cover 46 states all over the country. So those are logos, from different AI institute and also the geographical distributions. So to be briefly introduce our vision of what we call Athena, which is the name of the AI Institute, we envision that in the future, people are going to decouple the facility and also the services of the next generation networks. So the AI will be used as a powerful tool to address the challenges facing the mobile networks, such as operations. And also this large, the deployment of the edge devices and also the system will advance the state of the art of the AI regarding the functionality, efficiency, heterogeneities, and also the trustworthiness. In addition, this vision will also trigger the new modality of the AI in general, enabling a shared intelligent network infrastructure and also disrupt the ecosystem and the business models. It's basically going to diversify the services running on those networks and allow the smaller vendors to run their services on top of this, like we're renting all the facility. So to echo this vision, we launched this AI Institute was, actually now it's 8, but used to be the 7 institutions, including the Duke, MIT, Princeton, U, Wisconsin, Michigan, and also NCNT, and also several industrial partners and the several educational partners. So those are the 29 PIs in our senior personnel, if officially in our institute working on the different tasks. So we have very healthy and diverse background in terms of the technical expertise, and others, and also spreading over the different career phases, and we show here. So there are 4 research squads integrated. The first one is AI for edge computing, because all the AI institutes are centered around the AI technology developed for the different applications. We're going to develop the AI technology to fulfill the need of the next generation networks. And also we have a AI-powered computer system, which is going to supply the capability we're going to use for these AI technologies, including the efficiency, availability, and security, and also provide a system-level support. We also have the AI-powered networking system designed to provide a mobile network, using the data-driven approaches. And then finally, we have the services and application powered by the AI to develop the innovative services and application for the next generation network. So we have our education, the workforce development component, including the pre-college and college and the post-college phases, by collaborating with the K-12 educational institutions, the college, and also our PIs to provide different services. We also have our ambitious goal to broadening participation from the minority and underrepresented group, and we show here. And we have a quantitative measurement about the success of our education program. So there's some collaboration with the industry. We have a lot of industrial partners. They will directly or indirectly providing the support, and also place our students with the summer intern and also the employment placement, and our faculty members are visiting those industrial partners. We have an annual review meeting together with our members on those things. There are some external advisory board members from both industry and academia, and also even from international collaborating institutions. Okay, so this is basically the brief introduction about our AI Institute. Now let's move to the fun part, which is the research. I did not really have time to put our research interest of the whole AI Institute, but rather than we show some highlight from my group, many of them are collaborating with the PIs in the AI Institute to give people some ideas about how we are able to deploy the AI model at the different levels of edge computing, starting from the model itself, and then the edge devices and the system level. So let's start looking at how we are able to design an efficient AI models. So back to many years ago, people started to look at something called the pruning or the sparsity of the neural network, because people understand there is a redundancy which we are designing the neural network. It's not new. It has been there for more than 20, if not 30 years. However, if people play a very simple trick, just saying we're going to remove the width of the neural network, the value of which is smaller than some threshold, we are only able to achieve something called the theoretical speed up, which means we calculate how many calculations we need to perform the execution of the neural network. But if you deploy this neural network down to the real computer system, you will find out in many cases we're actually going to even slow down the computation rather than we save the computation time. So what happened here is if we just purely based on the values of the words, to remove those words of the neural network, then we're going to create a lot of holes in the memory layout which we use to store those words. So this is going to generate a lot of cache misses when we are trying to load those data from the memory hierarchy to the computing component. People know this. And people actually came up with a lot of solutions, trying to design some hardware to handle this, or people just, simply, manipulate those things in the library and redo this computation. About 2014 or 15, when we look at this problem, we are the computer scientists, computer system scientists rather than the computer science, computer scientists. So we realize, the troubles we have here is we did not really design this prune neural network, which means we remove those weights by considering how we're able to manage the data loading in the computer system. So when we're doing something we call the sparse neural network, or the pruning of the neural network, we need to consider, how we're going to lay out this data in the memory hierarchy, which means we need to introduce something we call the structural sparsity in the neural network even. So the idea is very simple. When we're doing the pruning, we actually need to prune the words which are stored in the memory as a whole block, or whole line, or whole row and whole column, so we can preserve the data locality. It's a very simple idea. So what we do is this. So we actually going to remove the data corresponding to the whole filters or the whole channels, or the corresponding position of the different filters, or even the whole layer, because we know those data are stored in our data block adjacent to each other. So by doing this, we're actually going to prune the neural network in the structural way, so that we can still remove the majority of the words, but can still preserve, the data locality stored in the memory. And this actually is going to achieve the positive speed up, without generating many cache misses. And you can apply the technology in the different application, not just the image recognition, but also do like NLP or any others, by applying the different constraints. It's a very simple solution. And now the structural pruning has been used almost in every single neural network optimization. This work has been cited more than 2,000 times. Okay, so but people actually came up with a lot of solution for this called structural pruning later on. This is another example from our group. You basically can just apply different regularizer on the words, trying to guide the removal of the words. This is one example to show you can apply something called the Hoyle square regularizer. I'm not going through the details, but this equation gives the different words, or the different preference to the different words of the neural network during the pruning, so that we can actually preserve, the large words and remove the smaller words. And by doing so, we are able to achieve the progress, pruning over the different epochs, and achieve the state-of-the-art, the pruning rate compared with all others back to 2020. Of course, people, progress more, after this. But we can do even more than that, because there is another parallel solution for the neural network optimization called the quantization. It's very simple. You have a lot of that, to represent the value. But in many cases, you don't need to have such a high precision during the inference. So what you can do is you have the quantization to use a smaller number of the bits to represent the weight, and still be able to achieve relatively good result. People have been doing this for also many years. So in 2021, actually, we actually trying to combine this structural pruning with precision or quantization. So what we did is we actually considered the bit in the way the bit to store in the memory, the column and the rows on the first. And then when we're doing the quantization, we are able to remove the whole columns or whole rows as what we did in the structural pruning. the granularity changes to the smaller value, which means each one column rather than one block. And by doing so, we actually kind to achieve, the different set of the quantization, such as you have a 4-bit. For example, originally, if you want to remove one row, one column, you can just remove the first one, the last one. Now this structural means the precision quantization will allow you to remove the column in the middle. And by doing so, you can achieve more aggressive, the quantization with, the relatively good performance. So the technology we use will be the exact same as we did in the spatial pruning, like we apply the Google lasso or any other things on those bits, and we can still be able to preserve the data locality and the structural storage, but we can achieve higher performance. Okay. So you can automate the things, because people also came up with some methodology for the neural architecture search to automate, the design of the neural network. So what people did is very simple. Rather than we can manually design the neural network, you actually can prepare a library of all the operators of the neural network, and then you are able to select, the operators from the library and combine them together to form the neural network. And then you can do the trial on the performance, evaluation of the combined neural network to see if, the performance of the designed neural network reached our goal or not. And then you can gradually optimize, the combination until we achieve our final goal. So you have a different way to do this. You have one for all. That's basically you design a giant neural network, at once, and then you select, some component to combine them together. Or you can have a predictor, to predict, the structure of the neural network and the corresponding performance, and then you gradually approach the final result. So people have done many work on this, but one example I'm going to give to you is called the skill NAS, which actually received the highest score in the AutoML conference last year. So idea is we're trying to design the visual system which allow us to automatically provide, the best performance for the objective with different skills. Can be very giant one with a lot of features, to be very small one, which have very little features we can recognize. So traditionally, you have to design, the multiple branches of the neural network with maybe the very dense connectivity between different layers, so they can prepare for the worst case for all the different combinations. But we are able to automate the whole design by gradually search for the optimal connectivity between the different layers and different branches, so that you can still achieve the highest performance. And many ways actually can be shared, during this process to basically remove the many ways of the neural network. So this actually the result is very good performance, and can be deployed actually has been deployed on the edge device designed by Qualcomm. So, but we can do more aggressively. So this is another example saying we can using the NAS, to optimize the neural network, which is used for the recommender system. Basically recommendation. So this would be very typical function for the web services, which guide you to click some web page. So we work with Manta to automate the design of the recommendation system, which was originally designed by the designers manually, so that to achieve the highest performance. There are some challenges because usually you see the very diverse structure of the recommendation system, and the interaction between the different components be very different from what we use in the image processing, and the connectivity can be very dense or can be very sparse, depends on which component we talk about. So I won't. I'm not going through the details, but this paper is going to publish in 3W soon. In the following months. And now we're working with Qualcomm trying to deploy this technique down to, again, the edge device developed by Qualcomm. So now let's move, our focuses from the algorithm or the model to the hardware, especially the in-memory computing, because I'm particularly impressed by the leading position of the USC in this area as our basically the dean mentioned this morning, especially this one picture from Joshua's work. So in-memory computing became very popular after we entered the neural network or the AI age. The reason is, there are many operations of the neural network on matrix of vector multiplications. And this application can be easily mapped, down to a structure we call the memory array. And also here, that's basically the memory register. Joshua is a pioneer on this, which is a device, the resistance of which can be programmed using the voltage of current, and it can be used to represent the weight of the neural network. So in 2012, Joshua and his colleagues in the HP came up with something called the memory register crossbar, which is a multi-input, multi-output system allow us to map, the computation of the vector and the matrix down to this structure, and each cross point will represent the one weight of the neural network. If you inject the current, you got to receive the voltage, and the voltage will be the sum of the products of each point. That'll be the natural, computation of the vector matrix of multiplication. Of course, you can also implement this one using the traditional device like a NAND flash or the ISRAM. So 2019, we worked with National Tsinghua University in Taiwan to finish one chip for the ARM-based computing in-memory chip. Over here, we basically vertically integrated a memory device on top of CMOS, and we test out the performance of the CNN or MLP or such kind of neural network on top of this, and receive good results. We are able to make the trade-off between performance and the power and the accuracy, by training the different designs and for the different application. There are some tricks how we are able to improve the performance and accuracy and the robustness by overcoming basically the defect or the variation of the devices. So in 2022, last year, SSCC, we published one paper in ISRAM, to implement the computing in memory, because ISRAM is more mature, but we remove the analog digital conversion part, which is really power hungry in the design. So the idea is we actually change the computation to the purely digital, and then we are able to use a simpler logic to mimic, but not mimic, to replace the function of the ADDA converter that you used in the past. So these are some comparison with the user last year. So last year, this work gave the highest energy efficiency for this, so we call the accuracy lossless, design with a bit, and you are able to actually fine-tune the voltage and also the operating condition to achieve the different performance and the throughput and so on and forth. Okay, so but we have been doing this actually for a couple of years, inspired by this memory register work, and this back to the 2015, we already started working on the architectural work, trying to integrate this memory register based computing in memory component to deploy the large neural network. This is one example to show at that time we started to develop our in-house compiler to identify the component of the different of our program and deploy this component down to this members of crossbar, maybe multiple of them, so that we're able to deploy the large neural network and also the multi-layer neural network into this design, achieve significant performance improvement, let's say tens or 100 times. So yeah, we actually designed it for the different applications in 2018. We actually mimic the behavior of the GAN, the generative adversarial neural network, engine, so that we can implement, the two engines simultaneously to mimic the generator and the discriminator. And this data path, there are many actually the common components that can be shared, and we can dramatically reduce, the computational cost as we show here. And in many cases, you just change the label and the output, but you still be able to reuse, the calculation output, from the pipeline. And also, there are many small tricks you can play. For example, in the Zaro, probably in 2019, we can actually handle this transport convolution, which we have a lot of insertions of zeros by computing the non-zero element first, and then we insert a zero element to induce the result. Because adding value times by a zero will be a zero. So by doing so, you can dramatically reduce the computation redundancy and improve the performance. And you can also apply the similar computing in memory structure to the transformers, which I also thought some US colleagues presented. But the difficulty here is in the transformer computation, there's some intermediate matrix you have to compute. And if you really want to store those values into the memory, you actually have to program the memory with this intermediate result. So the key becomes you want to minimize, the writing operation of this intermediate result, or push them to the end of the pipeline, so that you're able to fully utilize the advantage of this processing of this computing in memory design. So that was exactly what we proposed, 3 years ago, a little bit more than 2 years ago, for using this processing in memory or computing in memory architecture for the transformers. But we also care about the optimization at the compiler and also the scheduling level. By working with AMD, especially on their latest GPU design, so we actually proposed the cascading structural pruning, the CISP, which was published in last year, ISCA. So the idea is we found the data movement energy in the sparse neural network is dominated by the redundant input activation fetch. We actually fetched that one. I found many of them actually not going to participate in the computation. So what we propose here is when we are pruning the neural network, we actually do the gradual or the cascaded pruning, so that if there's one input, the corresponding word has been pruned, then this word will not be able to show up in the later computation. So the number of the input features participating in the computation will become smaller and smaller, when we increase the number of the layers. And by doing so, we will have a much more efficient computation, which we show here. All this black bar basically show, we have to totally remove the input, so the input will not be participating in the computation in the following epochs. So that's all the layers. So that is our design. So the CISP, also allows input data reuse across the filter track within the each PE, so we can capture the reuse in the fewer extra raster bin, so that we're able to continue improve the performance. And the result basically showed, the accuracy loss will be less than 1%, with actually very high efficiency improvement, 3 to 5 times, with more than half, the power consumption, the reduction. Okay, So let's we have about 15 minutes. Let's talk about the system level design. I know a lot of people talk about the federated learning. We are also doing federated learning because when we solve the problem on the edge, the hardware and also the software, you have to connect all the devices together to make sure they can work collaboratively. So the federated learning people actually introduced is actually the special I won't say distributed, but similar the distributed framework was to allow all the devices to work together to contribute the data they are collecting, and also allow the server to or in the distributed way to train the model using all the contribution and deploy the model down to the different devices with possibly the personalization, to the different data of the devices. It has been widely used in the financial or the wide services or softwares. But one challenge is here is actually the communication cost and also the computational cost, because if you want to just train the VGG16 on the image light, give people one example, we have to have a 9,000 runs until the model converge with a parameter of 138 millions, and remember each parameter will be a floating point, so which means 32 bits, and we have to transfer about 500 terabytes on this the networks. It was only the one that is one. Not even talk about some other important factor like the statistical heterogeneity, like a non-identically distributed characteristic of the different data of the different devices, because for this data they are somehow related but not exactly the same. So we proposed we call the Fed mask. I think that work paper in last year's census to basically to reduce the communication cost and also computational cost. So what we do is actually to leverage the one for all network concept in the neural architecture search. So we have a uniform format neural network, which can be deployed from all the devices. But for each device, they're not going to use all this neural network. They only use the part of this neural network to participate in the computation. And by doing so, we can reduce the computational cost, but also apply what we call the personalization to adapt to this neural network to the different requirement on the different devices. But the mask basically is just 0 and 1, right? They tell us the way it will be used or not. So the mask actually have a large number of the element, but each element just the binary. And so what we're going to do is actually we're not trying to train the original large neural network, rather than we just train the mask, because we find out the redundancy of the mask is so large, so that allow us to train some patterns which give us the good performance to basically when we perform the mask the neural network on the different devices. So this is actually one example to show here. And when we're doing the communication between the device and also a central server to do the training of this mask, we actually only communicate the mask to the server, but rather than we communicate the whole neural network frozen width to the central server. And we can dramatically reduce the computation cost. So how we're able to do the aggregation on the parameters of the mask. This is one example. So if we have if there is only one channel corresponded, the words for one device, but we don't have this corresponding layer, corresponding component for any other devices, we just directly inherit the whole thing down to the aggregated neural network. But if we see there are two devices, they share the same width, then we're only then we're going to do the aggregation. So basically we're actually going to XOR on this binary value and then put to put to the shared training mask. That's how we're going to do this. And you, as we show here, they have a frozen local model. They're the same for all these devices. But we have a heterogeneous the binary mask, and for each devices, they have each device they have a different binary mask, which is a highly personalized, for the different device. And some of the words are aggregated as a central server, some of them are not, which means those servers, those words are representing the personalized performance of the neural network. And the personalized model will be the mask, the frozen local model, as we show at the bottom rows here. And this is basically a good combination and trade-off between the personalization, the connection cost, and also the computational cost at edge. We actually built up the experimental system in our lab, with all the different devices. We're now expanding to more the different types of devices, including the Raspberry Pi, the Jetson TS2, the Jetson Nano, or the computers, the different phones. And all they're connected with either Ethernet or Wi-Fi or the 4G, 5G with different connectivities. We try out to see how those things can affect the performance. And this evaluation will show the EMNIS, the CPR10, the HAR, the Shakespeare, which are the common data set used for the federated learning with a different baseline. I'm not going to all the details, but I want you to pay attention to something we call the BN fed average, the binary neural network with a fed average. The fed average is a popular federated learning framework which allows us to do the aggregation among the different neural networks. And the binary neural network is actually the simplest neural network. It's a weight of the neural network of binary because we feel like it's be comparable precision to our binary mask, right? So, but usually the binary neural network is hard to train and also suffer from the low accuracy. If you look at the memory usage, which is also the one of our major motivation to use this binary neural network and also the binary mask. So the fed mask, have a slight, has a fewer number of the, I would say it's a smaller memory footprint compared with the baseline model, but maybe the 10 times larger than BNN because BNN only store the binary values, but now we need to store the floating point value for the frozen neural network and also the binary mask together. And also, if we look at the inference speed up, so we actually have something in the middle too. We have certainly I would say the 1.5 times, speed up compared with the baseline, but still, the binary neural network which give us the better performance, but with much worse in accuracy. We have the proportional energy saving compared with our baseline and the fed mask and also the binary. So this would be the good example to show our federated learning work. But there are many others. I just pick this one because this should be the good example to show how we can consider the communication, the computation, and also the edge. So the first. But we're also doing like the data bias, the fairness or the privacy or many others. So this be the roadmap. We start looking at this back to 2012 when Joshua, the HP groups, started to present people saying you can do this. And after that, we map this one down to the crossbar. We figure out this the design, and we start to build our chip. And from the chip, we're trying to optimize the algorithm, which will be the hardware friendly to our design. And we design a computer architecture to adopt to this design and then move to the system level to connect this processing element together or the ID device together. So now we think we have a full stack solution for all the different it's a data types and the models as many other colleagues in USC are doing. I think I'm going to stop here and open to any questions you may have. Yeah, thank you.
Great, thanks, Yiran, for covering both your AI Institute and also the interesting topic in your own research group. So we have questions. Let's first see from the audience. Any questions you want to ask Yiran? Oh, well, you are thinking. We have some questions in the Q&A chat. So the first question is, in the array-based computing in memory, did you observe efficiency issues or challenges when trying to scale the size of each array crossbar and when creating combinations of smaller arrays with NOCs?
Yeah. Okay, I can maybe try to answer this question first, then for the second one. So this is a very good question, and that has been bothering in memory designer for almost a decade, if not longer. So the issue is, we have something called the area efficiency in the memory design, which means, if the memory array is larger, we usually have a relatively smaller peripheral circuit. And that's going to give us the higher efficiency, computing efficiency, and also the area efficiency. However, in some computations, especially in the spots, the processing, we need to deal with, the data with a smaller array. This gives us a combination between the larger array, smaller array with different efficiency trade-offs. So one example, as we published, recently, is using the in-memory computing for the recommendation system using smart SSD, because what we did is you have to have a smaller array to process the embedding and the larger array to process the deep neural network, and the peripheral circuit, especially the ADDA conversion, going to eat up the majority of the power consumption and the hardware cost if we have many smaller array. So what we did is have actually allow many arrays to share the limited number of this peripheral, source circuit, and find a way to smartly schedule the computation distributed to the different smaller array, to make the trade-off. So that's the one way we did. But of course, there are many other ways you can do, either in the spatial or the temporal part of them, or the sequential, or the scheduling.
Good. So okay. So the second question, with regarding to using systolic arrays, PE arrays, how do you see their value or role in the future when one considers 3D heterogeneous integration?
Yeah. It's actually a very important topic too, because if we talk about the 3D heterogeneous integration, will allow us to give more connectivity to this systolic array or P array, and depends on how you're going to design those things, you may or may not improve the performance. One example is the systolic array, right? We rely on the internal data flow to optimize the computation, and we only care about the input and output. But in the P array, we need a more finer, the guidance for this data flow. We recently with the Cypress, on this wafer level design, we have a design very complicated scheduler trying to guide the data flow on the whole wafer, and you can imagine we can only fit in the data at the periphery. but we need to somehow manage all the data flow with the whole wafer to give us the much more difficult challenges on this one. But the 3D heterogeneous integration will be able to solve the problem because allow the data to fit in the middle. I think that's be very promising technique to solve the problem. Yeah.
Great, thanks. We have a minute for one short questions if anyone has. Okay, so Yiran, so for the computing in memory, using SRAM, you show great performance. Those are excellent. But if we consider edge applications, we also probably want to have the non-volatility property, right? SRAM is volatile. So how do you any comment on that or solutions you're considering?
Yeah, trust me or not, the first commercial success of this percent in memory is not because the smaller die size or the performance or the power efficiency, actually based on the non-volatility, because people trying to integrate this one to the product which can provide a longer standby time. So the non-volatility is actually very important from the commercial perspective. Yeah.
Yeah. Okay. Great. Okay. So thank you, Yiran. Let's move on. And our next special presentation will be given by Steve, as I mentioned before. Steve, whenever you're ready.
Thank you, Joshua. One more question came up for the last speaker. Do you want to cover that before you came on? It's in the Q&A, or do you want to?
Okay. Yeah. Maybe you can answer it in the.
I can type.
Yeah. Type. Yeah.
Okay. Okay. Sounds good. And Yolanda, is somebody going to display my slides for me? Or otherwise, I'm happy to. Or Joshua.
Yeah. I do. Who can?
Yes, you can do it. You can do it yourself, Steve. I'd be happy to do it if you'd like.
Okay. No, I'll do it. I can do it in PowerPoint then.
Perfect. Thank you.
Okay. Well, thank you very much, everybody. I'm going to give a different kind of a talk today, and thank you for those of you who can stay at the end of the session today. But I'm going to talk about opportunities for AI on the edge under the DoD Microelectronics Commons program. And so I'm going to be talking about a funding opportunity rather than a research agenda. And it sounds a little bit more like a talk that a sponsor would give rather than a researcher. But the reason I'm giving this talk is because USC led a proposal to this program. And if we are fortunate enough to be selected to run one of the hubs, and I'll tell you a little bit later what that means, we will have the opportunity to bid on projects with collaborators. And so there will be opportunities for some of you that are listening to this talk to get involved with what we're doing here if we're selected. And some of the people here on the panel, like Joshua and Tony Levy and Peter Burrell, were also involved in this proposal. And so was Adam Stieg, who I've seen in the audience if you're still on, from UCLA. So just need to adjust my Zoom so it's not blocking my screen. So what the DoD Microelectronics Commons program is about is lab to fab transition. So it's not a typical fundamental research university-based research program, but it's about bridging the valley of death and building domestic capabilities that are useful to the DoD involving microelectronics. And it's a focus on laboratory prototyping and making sure that the kinds of laboratory prototyping that universities do can transition into fabrication facilities run by industry or other sorts of partners that produce things that are useful to the Department of Defense. So these first few slides I have borrowed from Dave Shenoy, who works in the Office of the Secretary of Defense and has helped formulate this program. And I didn't put dollar values on the slides, but this is a $2 billion program, billion with a B, that will run for 5 years. The funding has been appropriated. And so it's a very large scale program that will have many funding opportunities and should have a big impact on the microelectronics industry in the United States, in particular for the DoD. For those of you who have heard about the CHIPS Act and the funding under that, it's about $52 billion that was appropriated, and 50 billion of that goes to the Department of Commerce and is largely focused on industry and commercial foundries, but 2 billion has gone to the DoD, and that's what this program is about. So it's a relatively small part of the CHIPS Act, but a small part of the CHIPS Act is still a big funding source for the kind of research that we do. So moving on to the next slide, I mentioned that this is about lab to fab and making sure that innovation can have the effect that it needs to have. On the left of the slides are a set of barriers that are currently in place that prevent technology from getting from university labs into DoD systems. There's a lack of access to fabs for prototyping. There are high capital costs for building things in hardware in microelectronics, as many of you may know, for those of you who are working in hardware. The cost of the intellectual property, the libraries, and the tools that are needed to do these kinds of designs are very expensive, and so that's a big barrier of entry. There's a problem with packaging. The US essentially has no leading edge packaging capability to support the integration of microelectronics. And as Moore's law comes closer to an end, this packaging is becoming more and more important, and we just don't have this manufacturing capability in the United States. And we don't have as many people working in this area to support the needs that the department has. And in fact, this is an interesting forum because one of the reasons we don't have enough people in microelectronics is because AI and computer science is taking so many people who are interested in STEM. So we need more people in STEM in general, but we also need people who are interested in the hardware platforms that enable the work that we're doing in machine learning and the other work that's so important to applications and systems. And so a forum like this is the perfect kind of forum to attract interest for those who are interested in AI, but are interested in how to make AI relevant on the edge and the hardware platforms that will enable that. And so I won't read through the end states on the right, but these are all the kinds of things that the program wants to address through the funding in this program. So here is a slightly more technical slide. I talked about the Valley of Death, and we have technology evolving on this slide from the left-hand side, where we have proofs of concept and the kinds of things that are typically done in research universities and can also be done in startup companies. And these are the more typical kinds of research programs that many of us in universities think about that are sponsored by places like NSF or DARPA. And then on the right side, we have commercial industry and the defense industrial base and defense programs that need to adopt more innovative technology to meet the needs. And this program is meant to fill in this Valley of Death that's in the middle. And they are interested in addressing this problem in 6 different application domains that are listed here. And these right arrows highlight the 2 areas that are most relevant to the topic of today's workshop. And I'll tell you a little bit more in a few slides about the proposal that we did from Southern California that USC led that actually focused in the areas of electronic warfare and 5G, 6G. So slightly different than the emphasis here. But even in electronic warfare and 5G, 6G, there are opportunities for AI in the backend processing for these applications. And the other thing that's important to know is that if we are selected for this program, although our proposal focused in those 2 areas, and we will either be selected or not based on the strength of our proposals in those 2 areas, if we win, we will have the opportunity to bid on projects in any of the 6 areas. And so if we're leading a hub, if you're interested in collaborating with us, we should have opportunities in these areas. So this program has an interesting structure, and the hardware capabilities in this program are composed of hubs and cores. USC has led a team that makes up a hub, and a hub is a network of regional entities with lab prototyping capabilities, microelectronics talent, transition capabilities, and also has a set of fabrication facilities. And so in Southern California, we have formed a team that includes the 7 major research universities in Southern California that are between Santa Barbara and San Diego and east to Riverside. So that includes all 6 of the UC campuses in that region, as well as Caltech and USC. Each of those universities has a significant size nanofab facility that supports not only internal researchers, but external users. And then we have 3 DoD scale industry fabs at Northrop Grumman, HRL, and Teledyne. And I realize I'm getting ahead of myself. I have another slide that talks about this. But a hub is a regional entity. And many of you are in Southern California, many of you are at USC, and so you're part of our region. And regions are not defined strictly. And so if you're outside of Southern California, but collaborate with institutions in Southern California and bring a unique capability, you can join our team when it comes to submitting project proposals. And then we're also working with core facilities, which are defined on the right, which are throughout the country. So for example, we don't have a commercial silicon foundry, a large scale commercial silicon foundry in Southern California. And so under this program, we can work with companies like Global Foundries or Intel and Skywater and others who do have those capabilities, and we've set up those collaborations. So there are lots of connections for fabrication within this network. And then I've already mentioned, but the proposal that we put in for a hub is for $100 million over 5 years. So it's a lot of effort just to put together a hub. But we expect funding at a similar order of magnitude for projects if we are awarded a hub. And only hubs are allowed to bid for projects. And so if you're not part of a hub today, membership in hubs will be dynamic. So you'll have the chance to work with us if you have interesting ideas to bring. And there will be lots of opportunities, as I've said, in all 6 of those application areas. And so we hope to have the chance to work with many of you on these projects. The projects are for hardware demonstrations that take advantage of this lab to fab capability. So they're not blue sky research programs, but they are projects that are meant to take an idea that's already been demonstrated at some small scale and to take advantage of the fabrication facilities that we have in our hub to provide a DoD need. I'm getting a little bit short on time, but in the area of AI hardware, the government has particular interests in solving their challenges. And I have 2 slides here on the gaps and opportunities that they've identified. They're interested in AI computing throughput and energy efficiency, multi-domain sensor problems and integration of sensor data. They need to be able to rapidly adapt to change. So think about AI in the field operating in real time on computing architectures and supporting decisions for warfighters in complex environment, and emerging architectures that address real-time applications and high performance at scale. They're interested in neuro-inspired design, AI hardware, many of the kinds of things that we're talking about today. They're also interested in co-design, materials and fabrication, CMOS and what comes beyond CMOS, and also testing and measurement. So I mentioned that we put together a hub in Southern California with all the major research universities. We also have a workforce development component that includes Pasadena City College, National University, Morgan State, North Carolina A&T, and Cal State Fullerton, which isn't on this slide, but is a part of our team. We have lots of commercial partners. Here's a more schematic view of our team. I know it's a very busy slide and lots of logos, but it's really an amazing team that we've had come together here. And we're thinking about fabs at 3 different levels of prototypes: lab level prototypes, small scale DoD prototypes, and large scale commercial prototypes. We have lots of capabilities here, and the way we're pulling all this together is with a reimagined Moses team. that will help users navigate this vast array of services that we have in the region, and will provide IP and tools and everything that you need to do these hardware prototypes. Here's another view of what Moses will be doing, and we have some ambitious goals about the timescale in which we can do these prototypes to make sure that we can foster innovation. And I think I will stop there since it's 12:15, but I'll be happy to take questions.
Thank you, Steve, for your heroic effort in leading this hub proposal and this very informative introduction. Any questions to Steve? Yolanda, you have a question to Steve?
Yes, Steve, you mentioned that a major motivator is to increase the workforce capabilities. And so, you know, everybody's very interested in natural language these days and robotics and such things. So I found the talks today incredibly compelling, very exciting. How do we connect students and professionals into these research areas better? What are there ideas in your discussions about that?
There are ideas. It's a complicated question, and we don't have easy answers. But we have a number of approaches that we'll implement if we get funded under this program. We're open to new ideas. Ideas include teaching courses that allow students to actually fabricate and build technology within the course of a semester, which is a challenge today. We have the Moses service and we have access to commercial foundries, but it's expensive and it takes a long time. So a chip tape out can take on the order of 8 to 12 months. And so how do you fit that in a semester? So we're interested in ways in which we can turn around designs in a semester. We're interested in free tape out programs. We're interested in community college programs. There are cohorts of community college students who are on track for 4-year universities and beyond. And so we want to reach those students and take advantage of their interest in STEM and their academic capabilities and get them interested in the hardware aspects of it. Other hands-on opportunities, not just with respect to fabrication, but people seeing the fun that we can have when we build things and make things work and put things together that work in the field. So it's a big job. It also has to do with expanding our recruiting efforts so that people from underrepresented groups see the opportunities that are here. We have lots of untapped talent that isn't being brought into these discussions as much as they should today. Mm-hmm. Those are just some of the approaches, but you may have other ideas too, and we'd love to take advantage of them.
Thank you.
Great. Yeah, thank you. So I guess this conclude our first day symposium, and tomorrow we will have another half-day symposium, and we will be discussing interesting topic on hardware, software co-design, and also post-CMOS hardware. And also follow that, we will have a panel discussion. Hope to see every one of you tomorrow, and have a nice rest of your day. Yolanda, anything you want to add?
That's it. Thank you so much.
Yeah. Okay, great. See you tomorrow. Bye.